Dear learners, welcome to the course Electromagnetic Fields. In this video, we are going to look about the course outline of electromagnetic fields. Let's start the discussion with the definition of electromagnetic. What is electromagnetic? Electromagnetic is the study of electric charges at rest and in motion. This is nothing but we are going to discuss about the electric field and magnetic field. From the elementary physics, we already studied there are two types of charges exist. One is positive charge and another one is negative charge. This figure it illustrates the electric field lines, and this figure it illustrates the magnetic field lines. When the current flowing through the conductor, there will be a magnetic field around the conductor. So when the charges are in motion, this is nothing but the flow of current. When the current is flowing through the conductor, magnetic field will be surrounding the conductor. So we will discuss about both the nature of electric field and magnetic field under the course Electromagnetic Fields. A field is a spatial distribution of physical quantity which may or may not be a function of time. A time varying electric and magnetic fields are resulting in an electromagnetic field. Under certain conditions, time dependent electromagnetic fields produce waves that radiate from the source. This figure illustrates the existence of the gravitational field between the free falling object and the earth. There is no string is connected between the free falling object and the earth. For instance, we learned from elementary mechanics that masses attract each other. This is why objects fall toward the earth's surface. But since there is no elastic strings connecting a free falling object and the earth, how do we explain the phenomena? We explain this action at a distance phenomena by postulating the existence of a gravitational field. This figure illustrates the possibilities of satellite communication and of receiving signals from space probes millions of miles away from can be explained only by postulating the existence of electric and magnetic fields and electromagnetic waves. Electromagnetics is of fundamental importance to physicists and to electrical and computer engineers. Electromagnetic theory is indispensable in understanding the principle of atom smashers, cathode ray oscilloscopes, radar, satellite communication, television reception, remote sensing, radio astronomy, microwave devices, optical fiber communication, transients in transmission lines, electromagnetic compatibility problems, instrument landing systems, electromechanical energy conversion, and so on. This figure it illustrates so many applications of electromagnetic fields in our day-to-day life. So from this we can easily understand the importance of electromagnetic fields in our day-to-day life. Now we have one question. Already we have studied circuit theory and so many things. Then why we go for electromagnetic field theory? I explained the need of electromagnetic theory with the help of this illustration. This figure illustrates a monopole antenna of the type we see on a walkie-talkie. I hope you are all seeing the walkie-talkie. On transmit, the source at the base feeds the antenna with the message carrying current at an appropriate carrier frequency. From a circuit theory point of view, the source feeds into an open circuit because the upper tip of the antenna is not connected to anything physically. Hence, no current would flow and nothing would happen. This viewpoint, of course, cannot explain why communication can be established between walkie-talkie at a distance. Electromagnetic concept must be used. When the length of the antenna is an appropriate part of the carrier wavelength, a non-uniform current will flow along an open-ended antenna. This current radiates a time-varying electromagnetic field in space, which propagates as an electromagnetic wave and induces current in other antenna at a distance. In this way, we communicate. So now you could understand the need of electromagnetic field. Next, we are going to see about the topics inside the syllabus Easy 8451 Electromagnetic Fields. Totally we have 5 units. The first unit is Introduction about Electromagnetic Fields. Under the title Introduction, we will discuss about the basic things: electromagnetic model, units and constants, and review of vector algebra, coordinate systems, line surface and volume integral, divergence, gradient and curl, and divergence theorem, Stokes theorem. These are all the basic things we will discuss under Unit 1. In the Unit 2, we will talk about the electrostatics. Electrostatics starts from Coulomb's law, and we will discuss about the applications of Coulomb's law. This is nothing but we will derive the electric field intensity and flux density for various configurations. That means various type of charge distribution, and we will deal the Gauss law and applications, boundary conditions, capacitance, and so many topics under this electrostatics. And Unit 3 will see the nature of magnetic field. Title of Unit 3 is Magnetostatics. Under this, we will talk about Lorentz force, Ampere circuit law, Weierstrass law and its applications, inductance, boundary conditions for magnetic fields, magnetic force, magnetic energy. Now we have the basic idea of electromagnetic fields. Then we have the knowledge about electric field and the magnetic field. Then we are going to study the time varying fields and Maxwell's equations. Mainly we focus on Maxwell's equation. There are 4 Maxwell's equations. We will study the Maxwell's equations in both differential and integral form. And in next Unit 5, title is Plane Electromagnetic Waves. Under this unit, we will discuss about the plane waves in lossless media and lossy media. And also we will discuss about a reflection of uniform plane waves. So we start from introduction, basic of electromagnetic fields, then slightly move on to electric field and magnetic field. Then we will discuss about the electromagnetic fields, and finally we conclude with the electromagnetic wave. This is the flow of this syllabus. These are the books I have referred. These 2 textbooks. Most of the topic covered in these 2 textbooks. One is David K. Cheng, Field and Wave Electromagnetics. Another one is W. H. Haidt and J. A. Buck, Engineering Electromagnetics. These are the other reference books for this course. So basically, this subject needs mathematics and engineering physics. After completion of a course Electromagnetic Fields, we can apply the knowledge in transmission lines and waveguides, antennas and wave propagation, RF and microwave engineering, and so many other communication subjects. It will be very helpful in understanding the concepts. Thank you.